Hello students, I am Tanmay. I welcome you all in my channel Chemistry of Molecules. So today we will discuss about an important reaction for basic understanding, that is allylic halogenation, and mainly we will discuss about chlorination and bromination. Today's discuss will cover few points, for example the basic concept from thermodynamic point of view of this reaction, second the mechanism of this reaction. In next, I will explain about the different variety of reagent could be useful for this bromination and chlorination. Especially, I will focus on NBS, N-Bromosuccinimide, and chlorination and bromination, little more details, and finally, I will discuss some example. So today's discussion will encounter all these points. So let's start. And one thing I want to say that these reactions you can write very easily, that you can memorize and do, but if you understand the basic concept, it will be very helpful to keep it in mind, because lots of reaction you have to memorize. So I suggest you just read this video completely, and I guess you will know lots of chemistry concepts. So let's start. So the main reaction actually is, today's topic is allylic halogenation. Okay, so the reaction is, this is a propene, this is halogen, and actually we will not always use halogen, we will different reagents also. So this is you can consider it as a source of halogen. Okay, so this reacts with this propene to produce this allylic halide or allyl halide, whatever you say, and 1 unit of HX. This is the main reaction. Why this is allylic? Because this position is called allylic position. Okay, that's why this is called allylic halogenation. And actually this reaction proceeds through mainly radical. I'll explain why. And in case of this NBS derivative, this part, this reaction has a unique name. Its name is Wohl-Ziegler reaction, that is bromination using N-Bromosuccinimide. Okay, so this is named as Wohl-Ziegler reaction. So please keep this thing in mind. It will be means this is the basic background introduction and the basic concept from point of view. If we see that we are watching that alkene is added to, means halogen is added to allylic, but we have previously read another reaction, that is, for example, you can see this is this X2, it produces simple this is X, this is X. This is actually, you can say, substitution type reaction. Substitution reaction, because one H is substituted by X. Fine. And this is addition reaction. This is addition reaction, and we know in a previous video I have explained the addition of halogen in details, and it happens through the formation of a bridge halonium cation. Means, what do I mean? Initially it produces, for example, if we take bromine, it produces bridge bromonium cation, and another anion is there, and which can attack and produces, which can attack this position or this position, and ultimately produces antiproton, transpoton. Fine. So if you see here, one molecule plus one molecule producing, means two molecule reactant producing two molecule of proton, and in this case two molecule of reactant producing one molecule of proton. So this reaction is entropically favorable. This is entropically favorable. Entropically favorable. Okay. This reaction, you can see this here one pi bond is broken and two sigma bond is formed. So lots of energy released. So enthalpically this reaction is favorable. Okay. So enthalpically. So if we consider the Gibbs free equation delta G equal to delta H minus T delta S. So you can see here entropically favored, this part, but this is entropically unfavored, this is enthalpically favored. So that is the main difference between these two, and this is the background idea how to carry out this reaction selectively. What I am saying? Since this is entropically unfavorable, that's why, means this is, and another thing, for addition, here see, for addition 2 molecule of reactant producing 1, so if we reduce, means low concentration, if we take low concentration of this halogen, then this part will be unfavorable because 2 producing 1, fine, but if we do low concentration, this will not be that much problematic. So that is the reason one, to maintain the low concentration. Second, if we consider the bromination reaction, this bromination is carried out in non-polar solvent like carbon tetrachloride, bromine, and bromine is taken in large amounts. So what happened? This one bromide anion in presence of another bromine produces this polyhalide anion. So, and it is stabilized because compared to Br minus is Br3 minus is directly more stable. So if we take less bromine, then stability of this will be affected. So all this point of view indicated, if we want to carry out this reaction, we have to stop this reaction or reduce the chances of this reaction. And what we can do? We can do this in presence of less amount of halogen first. Second, so second point is that we can take initiator, radical initiator. What do I mean? As I told that this reaction goes through radical, so we can use a radical initiator. Generally it is observed that this bromine, for example, Br2, undergo in presence of heat or light, you can say, it undergo cleavage to produce this radical. Why I have given equilibrium is left side? Because radicals are reactive species. They don't like to remain in radical form. They want to react, and the most probable chance for reaction is their combination to produce this. That's why. But since they are more reactive species, they undergo reaction very easily. Means they undergo reaction with some substrate producing this. So this is the mainly background thing. Now I will explain how this reaction happens. So till now what we have learned that low concentration of halogen and radical generation favors this reaction. Fine. So what we can think, let's consider the chlorination. Chlorination part. So what is observed, if we take propene, for example this propene, and take chlorine around 500 degrees centigrade, then it produces allylic chloride plus HCl. Okay, 500 degree centigrade part you can understand from T delta S point of view. If we increase T temperature and delta is already here neutral, you can say 2 molecule producing 2, so the reaction Gibbs free energy will be negative and this reaction will be favored. Fine. But if we take less than low concentration, then there is a chance of addition. Okay. Okay, so this is the chlorination. Okay, so you can see the mechanism is that is happens in presence of light or heat and in presence of radical initiator like diperoxide. This ROR you can consider is a means peroxy ether. Okay, this is a peroxide and this is AIBN as a isobutyryl or nitrile. Ultimately both produces radical. Okay. And this radical we can consider as a R dot. So this radical, and in this case for bromination process we use bromine or NBS as a reagent. For chlorination we can use chlorine and thionyl chloride as I have given example of chlorine. So this thionyl chloride also decomposes and produces chlorine radical. So what happens? This X produces these are in presence of this radical condition or heat. What produces this X dot, 2X dot. So they can combine, as I told. What they can do, instead of combining, they can further react with the alkene. So they can react with the alkene and produce allylic radical. What do I mean? Means from here it will abstract one hydrogen. This. So it produces this and this is called allylic radical. This is allylic radical and this radical is stabilized through resonance. How? So if we draw the resonance, this comes here, it comes here, it comes here. So this. So actually this double radical is now delocalized and that's why this is relatively stabilized. If I say stabilized, don't consider it's a stable, it could be no, radicals are not stable. Actually radicals are unstable. They are 7 electron species. Okay, 7 electron species. But due to this resonance, they are relatively stable. Okay, so okay, fine. So next what happens? That it reacts with another X. How? This gives one, and keep it in mind for radical we use fish hook arrows. These are fish hook, means one half arrow you can consider. So this and what it produces? So this is X plus X dot, and in this way chain continues. Chain continue. Okay. So the first step, this is the radical initiation. So first step, this is the initiation, means this. This is the initiation. This is the this part is propagation. Okay, in this way reaction continues. So this is the radical initiation mechanism. Now, the question is the most important part. We will discuss about the different variety of reagents. Okay, before going to that, I want to give you one special example. Just think. For example, instead of propene, if we take a different substrate like CH2, CH3, CH double bond CH2. Actually, this is not propane, this is 1-butene. Okay, so if we do the same condition, X2, H nu means radical production or radical means H nu or heat. This peroxide means radical initiator. Radical initiator. Think what will be the product? Means what this will also react because it also has allylic hydrogen. So what will be the product? So as you can see from the picture, the simplest answer will come. Okay, what will be the product? Product will be this CH3, CH double bond CH2. This will be the halogen. For example, this is X. Fine, but this is not only the case. What it will produce along with this? It will produce CH2, sorry, this is CH, then double bond CH2X. Now question, how this is produced? Just think about the allylic radical. So what it will produce? It will initially produce the allylic radical. This radical, and as I told, it can undergo resonance. So it can undergo resonance means CH3, this CH double bond this. So now this can undergo, this can react with 1X to prepare same. This can undergo. So here this will attack and here this will attack. Okay, that's why two products. So be careful. Propene, this radical is symmetrical radical. So this produces a symmetrical radical. That's why. But this is unsymmetrical radical. This is unsymmetrical radical. That's why these two types of product is obtained. Okay? Okay, fine. Now, in this context, you may have few confusions. Why? Because as I told, radical is produced. Some people may think, okay, radical is produced, fine. Why it reacts with only allylic one, not the double bond one? it can react, logically it should react. So yes, it can react with double bond. For example, let's consider this 3. So if it reacts with the double bond, what will be the product? Means this X. So that will be CH3. This double bond attached to this X means X dot. So overall means X. Overall is a radical. Fine. This is relatively less stable. Relatively less stable. Why? And compared to that of this allyl radical, because this is resonance, this is resonance, but this is not. Why? Because from that you can think there is a CH3 radical could be here, or you can say radical could be, this is X, radical could be here. See, this radical has only hyperconjugation, so relatively unstable, 7 electron species, but this is relatively stable, so that's why reaction will not happen. Another thing, you may think that why this can abstract these hydrogens. Why allyl hydrogen? This or this hydrogen? If it do, then it will produce this CH3, CH. I'm not right. I'm giving only one example. You will understand. This radical. This is called vinyl radical. This one allyl. This is vinyl radical. This is also relatively more unstable compared to this even, because this is a no resonance is there. Allyl can undergo resonance but not, because this is in sp2 orbit. Fine. So please keep this factor in mind. So this is the sp2. And so we have discussed about the mechanism. Now we will focus about different variety of reagents, and mainly we will focus on this NBS. So why NBS and what is NBS? NBS is a very famous reagent, you know. This is named as N-Bromosuccinimide. I have explained little bit the role of NBS for the double means halohydrine formation. Okay, I have explained. Please go through that. In the previous video, the bromination of alkene. So NBS is N-Bromosuccinimide. This is. So this is a 4-carbon succinic acid that's corresponding amide and produced and bromide attached. What is the uniqueness of this reagent? You can see nitrogen is more electronegative, so this is delta minus, this is delta plus. This is the interesting thing. And second, as we have explained that low bromine concentration, low halogen concentration prefers the allylic one, and this exactly same thing is done by NBS. How it does? Because NBS contains some amount of HBr and bromine as impurity. So if it has these as impurity, means very less amount, and this is responsible for this. Why? Because this bromo, if you consider HBr, this is delta minus, and this Br minus, because HBr is a strong acid, can attack it and produce this. So what it will result? It will produce bromine plus this N minus, and this is resonance stabilized. How I can say that this charge will come here, it will go there, means O minus double bond N. This is, so in this way, this is, it has another canonical form by using this carbonyl. So that's the difference. So this is stabilized, so add in this way reaction start. So as impurity, it starts the reaction and supplies very low concentration of bromide. And another thing, in presence of, for example, this HBr, in presence of a light or peroxide, whatever, it produces bromo radical, and another thing, N radical. So this, fine. So let's focus on the bromo radical. This bromo radical, previously we have generated bromo radical. This bromo radical performs the same job and ultimately converts allylic halide and HBr. It produces, because as we told HX, so ultimately, because one hydrogen, this one hydrogen will be replaced. One hydrogen will be replaced and ultimately produce HX, and this H will be further abstracted by this, and in this way bromo radical will be generated. So in this way ultimately what it is produced? This is producing succinimide stable, and another part this is producing Br dot. So in this way radical generates and reaction goes on, and always low concentration of halogen is maintained. Okay, and if means in this way you can say, and another thing, less concentration of bromine, because its reaction produces bromine, that can also cleave and produce bromine dot. Same way you can explain the factor. Okay, so we have discussed about this NBS, part of NBS. Fine. And one thing you keep it in mind, sometime it happens, sometime it is reported that in case of this, we generally use CCl4, carbon tetrachloride, as a solvent, but this chlorinated solvent are not preferred. For that purpose, we can use, instead of that, we can use acetonitrile as a solvent also. So this is. So we have discussed about this bromination as well as chlorination and especially NBS. So what we have learned up to this discussion? This discussion we learned for allylic bromination, what we need? We need high temperature, means temperature must be high, and second, low halogen, low X. Find this part. So this is the two things we have learned. So based on this understanding, now we will discuss few examples, and then I guess it will be clear to you properly. Okay. Let's continue the discussion. Here you can see in the, for example, this is the example 1, 2, 3 and 4. Okay. So in the first example, what's happening? What is produced? Since NBS CCl4H new peroxide, simple condition. So what is expected to produce? Allylic halogenation at this side or this side, any symmetrical, no problem. So let's draw it. This is the bromo. This. And see, whenever excess those type of words not written, you consider only monohalogenation. You may think, why not di? Because excess is not written in the problem, so mono. Second, this is called quinoline. Okay, you can consider it's a pyridine derivative, means one benzene extra of pyridine. Okay, so it is basic because this lone pair is in sp2 hybridized orbital. It can act as a base and it is not involving the aromaticity. Please keep it in mind. So what can happen is base. So there are two hydrogen. So what can happen? This lone pair can abstract this base. It will come here. It will leave. Okay. So this is the elimination reaction, and what it will produce? It will produce diene. Okay. So this is the first example. Second. Second example is little interesting. Why it is interesting? Because see, first is chlorine and iodine. First, we have to think which will react. There are two halogens given, and both are halogen halogen molecules. So who will react? Chlorine will react. Of chlorine is high, so it will not. It needs electron more compared to iodine. Iodine is little less reactive. Okay, that's why. So what will happen? Iodine will act as here Lewis acid. So what will be the consequence? So iodine is acting Lewis acid. We know that benzene in presence of Lewis acid. For example, iron 3+. If you provide chlorine, so what will be the product? The product will be chlorobenzene, aromatic electrophilic substitution. Okay. So that's similarly here also this iodine acting as a Lewis acid. So the product here will be chlorobenzene. So iodine will act as so chlorobenzene, and actually specifically if you want to say that is HCl. Okay, because one hydrogen is replaced. And in the second example, see it is thionyl chloride and HNO. Thionyl chloride actually looks like this. This is the thionyl chloride, and I have told that this is also a chlorine radical source under this radiation condition. This is one example you can consider thionyl chloride as a reagent for allylic chlorination. Okay, it will act as a chlorine dot, means Cl dot producer. It will produce Cl dot, and that will, because as we have previously explained about propene, so this benzene is also, this toluene is also propene. How? This part. This is benzylic. So similar like that. So reaction will happen, and ultimately it will produce. Let's draw it here. CH2Cl plus HCl. Fine? Okay. And the next NBSCCl4 we know this is also allylic bromination so it will also be CH2Br. So this is a very good method for allylic bromination. Fine. So okay. Now we will discuss this problem. So problem number 3. You can see here we have given how to convert this into this style. So what would be the best way? As we have learned NBSCCl4 or thionyl chloride HNu, any reagent. So ultimately this, for example, NBS, because NBS is famous and solid, so that's why NBS is preferred. Okay. So and handling this chlorine chlorinated reagent is little hazardous. I also believe because they are more reactive. So it will produce this. So it will produce this allylic bromination, this and CH3. Fine. So this, and in next step, if you provide base like KOH alcoholic and heat, or you can use quinoline also, anything. So ultimately what will happen? This one proton will be abstracted by this base negative charge. So it will come and it will leave. So in this way there will be styrene. So ethyl benzene to styrene conversion you can achieve in this way. And finally we will discuss the last problem of today. Okay. So this problem is about, you can see this is a radiocarbon is given. This carbon is radiocarbon and you can see it's a double bond and this, and here only chlorine is mentioned, no radical initiator, no temperature, because allylic chlorination either need radical initiator or need high temperature like 500 degrees centigrade. So no one is mentioned. So what we will do? We will think simple chlorination. How? Chlorine bond, so it will attack, and this is radiocarbon labeled in order to prove where the reaction is going on. So this is CH3, this is CH3. Ultimately this CH2Cl, if attacked it will leave, so it will produce Cl minus and this is plus. Now question, this is radio 1. Okay. So now question, chlorine can attack in this, but that is difficult because of bulkness. Chlorine can't attack at this position actually because of bulk. Instead of that it can do one thing, CH2 there is another H. So it can abstract this and in this way it will come here. So in this way charge will be balanced. So what will be the product? Product will be CH2, this CH2, Cl, this is, and here CH3. So this is actually the same thing. So that's how this reaction happening. No, don't need to be surprised. This is a very easy example. Okay, and keep one thing in mind. We say that chloride is not a good base, this thing. Actually, this is not true. Even, fluoride is a good base because the charge is concentrated. Chlorine is not that much big size. Charge is concentrated. So they can act as a base only if there is no stabilization. How? If we use any non-polar solvent, then it is very difficult to stabilize them. So they may show enough strong basicity. Fine. So that is the overall discussion of today. So what we have learned, first allylic halogenation, bromination, chlorination, and what is the background concept, thermodynamics, delta H versus delta S and temperature. So increasing temperature results and in terms of radical initiator results allylic substitution compared to addition we have learned. And after that we have learned the mechanism, and specially we have learned a reagent that is NBS for this purpose, means allylic halogenation. And finally we have discussed about few examples regarding this allylic bromination with some contradictions. So I hope this is you have understood this, and if this video is helpful for you, please support my channel to grow. How? You can support by first of all subscribe my channel Chemistry the Mystery of Molecule, and please press the bell icon to get the notification of every single video I upload. Secondly, share this video among your friends so that many people will be benefited from my effort, and I shall feel very happy if many people get benefited from my little effort. So till now, see you in my next video. All the best. Stay happy, stay cool. God bless you.